Hey yo steel friends, it's your DJ Design aka Dr. Bats coming to you live from the home studio. Hope you guys are excited for this next set of learning. Specifically in this video, we're going to go over the design of steel tension members for the limit states of fracture, yielding, and block shear. Now, as engineers, design is like the coolest thing we get to do. Whether you're designing the next illest building in the world, or you're just doing a simple highway bridge, or even if you're just trying to make this video not so stupid boring, engineers love to create. And so, I hope you guys find joy in the design process. Now, I suspect many of you guys got into engineering because you love to create. Probably when you were younger, you like to build stuff, make something new, and that's eventually going to be permanent and then somehow better society. So that's probably how you got started as an engineer. Now, we're going to take a look at the design of tension members for steel. Now, there's not one way of doing this. So in design, a lot of times we have to take a couple different approaches, we have to try a couple different answers and see what we like best and do our best to optimize the solution. Now, even though we don't have one straight up design process, the general kind of beat remains the same. Kind of like music, if you have the beat down, you can head in the right direction. It's going to lay down a nice track. So let's take a look how we do that in design. All right, so like we said, we want to follow kind of a process so we have the general idea of how to tackle design. And so by the end of this video, I want you to be able to design tension members to satisfy the limit states of yielding, fracture, and block shear. Now, how are we going to do that? Well, we basically want to find the member that meets the design criteria that has the smallest area. Smallest area means smallest weight. So basically, we want to satisfy the design criteria that P sub U has to be less than or equal to phi Pn. Now, for yielding, that means P sub U is less than or equal to phi Fyag. I like to rewrite this in terms of the gross area. A lot of times when we start a design problem, we know what kind of loads we have on it, P sub U. We also know what phi is, and we have an idea of what material we're going to use. So we can put everything in terms of the area that's needed. That'll help us pick members that are efficient. We'll do the same with fracture, so P sub U is less than or equal to phi times F sub U times the effective area. And I'm going to rewrite the effective area there as the shear lag factor U times the net area. Again, we can solve for the area that's needed. So rewriting this, we'll get that P sub U divided by phi times F sub U times our shear lag U has to be less than or equal to our net section area. Finally, we need to consider block shear. Now, block shear is going to be P sub U has to be less than or equal to phi times, well, there was a long equation that had two parts to it, right? So I'm not going to write all that down, but we know, hopefully we remember that block shear equation where we were looking at fracture on the net tension area and fracture on the net shear area, and then also fracture on the net tension area and yielding on the gross shear area. Anyhow, that's a problem because now we have three different areas: the net tension area, the net shear area, and the gross shear area in which to rewrite this equation in terms of, right? And we're not going to be able to do that. So that's part of what I was talking about with design. We're going to have to tackle the problem from a few different solutions because we're going to need to come up with a member area. We're going to come up with a connection layout, and then we have to see if that connection layout is going to work. So I'm just going to write here, it's difficult to determine the requirements for each of these areas. So block shear will kind of be the last thing we check. We'll try to pick our members based on yielding and fracture first, and then go on to check block shear. Because of this process and because we have all these area requirements, we're probably going to have to iterate through to get to the optimum solution. We're going to be checking members. We're going to check those members to see if they work. They might not work. We'll have to try other members. If they still don't work, we might have to go back to our manual and select new ones. Another point I wanted to just mention out of Chapter D is the slenderness limitation. So this is just a guideline for really vibrations. It helps to keep unwanted vibrations from occurring in your system. So they suggest that the slenderness of tension members does not exceed 300. So that means L over R is less than or equal to 300, except for rods and hangers, because rods and hangers are designed to kind of be long and slender. L here is going to be the length of the member, and R is going to be the least radius of gyration. Remember, we used L over R, the slenderness, when we look at compression members as well. The radius of gyration here is the square root of the moment of inertia over the area. Here we'll use the lower moment of inertia if you're having to calculate R. Most of the times you can pull it out of the manual. We're going to check our member to see if it meets this slenderness limitation. It's not a requirement. It's a user note, so it's not like, it's required, but it's just general good design if we can follow that. All right, so we have to wrap ourselves around this design problem, so we got to take a moment to take a look at what it says. So basically, here we have a truss. And in the truss, all the truss members are going to be double angles. At each joint, the truss members are connected by 3/4 inch thick gusset plates. On the truss, we were given dead and live service loads. We're going to need to factor those to get our LRFD factored load. Typical detail at joint H, you can see it's going to be the double angle connection with the connection being 3 bolt holes. Those bolt holes are going to be 3 inches apart from one another, the last one being an edge distance of 3 inches. We're going to use the standard gauge distance. We'll talk about it a little bit later, but we can find that in table 1-7A for angles. We'll assume 3/4 inch bolts, standard holes, and that the longer leg will be attached to the gusset plate. All right, we are asked to just design member HI. Now, in a real design, we'd have to go through and either design the most critical member, or we'd have to design every member in the system. Now, if we think about the critical members, HI and GH are probably going to be the critical tension members along the bottom chord here. So along that bottom chord, those are probably going to we could probably use the same member for all of those, the same size for all of those members. All right, the first step is to calculate the required design strength piece of use. So this requires our load combinations. I'm just going to move quickly through this. We're going to follow ASC 7-16 for our load combinations. When we have only dead and live loads, combination 1 or 2 will control. In this particular instance, combination 2 will control. So we will factor our loads as 1.2 dead plus 1.6 live. We then move through a method of sections. So we go back to statics class. We pull out method of sections, come up with the most efficient way to solve for FHI. Remember, all the loads that are on this method of sections have been factored. So that means the ultimate force in the member will be 132 kips. Because this member will be a double angle, then each angle has to hold half of this load, or 66 kips. So I find it easier to just look at one angle at a time and design that single angle member for half the required design load. All right, so now that we have the required design load, we can go ahead and try to get a feeling for what kind of gross area our member needs, what kind of net area the member will need, as well as the radius of gyration required to prevent unwanted vibrations. So calculating our gross area, I start from our tension limit state. We said that P sub U has to be less than or equal to phi Pn. That means 66 kips has to be less than or equal to 0.90 times Fy times Ag. For an angle member, we will assume ASTM A36 steel. That is the typical grade for angle members. If we look that up in AISC table 2-4, that will confirm that the standard material for angles is A36. All right, so working out the math, we see that the gross area has to be greater than or equal to 2.04 inches squared. If we can pick a member that has greater than 2.04 inches squared of area, then we will satisfy the yielding limit state. We'll do the same for the net area. So we start from now our fracture standpoint. P sub u has to be less than or equal to phi pn. So that means 66 kips has to be less than or equal to, phi is now 0.75 for fracture, F sub u times AN, so that is our effective area. So we can go ahead and continue the calculations. F sub u for grade A36 steel will be 58 KSI. And then we have U times AN. Working through the math, we get that 1.517 inches squared divided by U has to be less than or equal to our net section area. Now, some designers like to just assume a value for U, and as you become more experienced and you do maybe a few different designs with angle connections, maybe you'll want to pick a value for U. If we take a look at table D 3.1 in AISC, we see that for 3 fasteners, we fit case number 8, so that would be U equals 0.60. Now, we're probably, because we have a decently long connection, so we have a connection length of about 6 inches, we're probably going to end up being a little bit higher than 0.6. We're probably going to be somewhere between 0.6 or 0.8. So you could just assume a value of U right now if you wanted to take a look in terms of the net section area. I'm going to proceed kind of with this, but instead I'm going to keep the shear lag factor on the right-hand side of this equation above. So I'm going to take that 1.517 inches squared has to be less than or equal to U times AN. And then I'm eventually going to set up a table here to help with the selection of a member. And in that table, I will have to calculate U each time I pick one of my members. All right, the final thing that we can do that's pretty easy to when we're selecting out of the manual is to look at the slenderness limitation. Now again, remember this is just a recommendation. L over R has to be less than or equal to 300. So our length from our given problem was 10 feet or 120 inches. So that means that R has to be greater than or equal to 0.4 inches for this member. And we can just, we can pick R out of the table, so that's nice to include as we're trying to select a member that will become a good candidate for this particular design, the design of member HI. I'll just remind you that we want to use the least value of R as we make this selection for any member. For an angle member, this will be the radius of gyration about the z-axis, or RZ. And the z-axis was the axis that led to the minimum moment of inertia. All right, now it's time to pick a section, so we're going to have to open up our manual and take a look through the tables to find members. Now I'm going to start by picking members based on their gross area. And if we recall from our previous calculations, the gross area had to be greater than or equal to 2.04 inches squared to satisfy our yielding limit state. So we open up our manual and we take a look. Now you'll have to look at all the different types of angles, the different sizes, to figure out which ones have greater than 2.04 inches squared. We find that the L 5 by 3.5 by a quarter is one option that has an area of 2.07 inches squared. And you can see there's another 4 options below that I found that all meet this criteria. So anytime that they were close but greater than 2.04 inches squared, I included them for consideration. Now I need to get some of the other properties from the table while I'm looking at my manual. So the thickness of this leg will be 1/4 inch. That's a given. We can then calculate the net section area. So we do our fracture calculation. This is going to be our gross section area minus the diameter of the bolt plus 1/8 of an inch times the thickness of the angle leg. and that gives us 1.85 inches squared. We can look up the distance from the plane of the connection to the center of gravity, so being careful to look that up in the table, and we get that distance is going to be 0.804 inches. We then can calculate our shear lag factor. In this case, our length of our connection was 6 inches, so my shear lag factor was 0.866. And then I have my effective area, which is my net section area times U, which is 1.60 inches squared. Looking back at the previous page, I see that value, U times AN, had to be greater than 1.517 inches squared to satisfy fracture. So I can see that this member I just picked, 1.60 inches squared, is greater than 1.517, so it'll work. Finally, I can get the minimum radius of gyration. That's going to be 0.761 inches. And so I see that that's greater than 0.4 inches, which was the requirement from the slenderness ratio. So for now, these 5 members will be the candidates for our design. Now, we know that these 5 members, as of right now, satisfy the yielding limit state. They also satisfy the fracture limit state. Again, you'll have to complete this table on your own to get all these numbers. But we see now that all of these would meet. Now, you could question the last section. The last section just barely meets the requirement for fracture, so maybe that's a little bit close to the limit. But again, we have our safety factors and our reduction factors, so this would meet the design as given in the AISC spec. All right, so now it's time to figure out block shear. That's the only limit state we haven't really explicitly checked, and it's the hardest to do on in a bulk capacity. So I'm going to now pick the lightest section to go through and try block shear. The lightest section has the lowest area, so I'll start with the 5 by 3.5 by 1/4 inch angle. All of these things are given. You can see I've entered in something called the gauge distance. This is the distance from the back heel of the angle to where the first line of bolts can be. And this is just a kind of a spacing requirement so that the bolt heads and the nuts will not interfere with the piece of the angle that's sticking out of the page. Remember, we have to get our tools in there in order to actually make this connection. I just want to go over kind of block shear. Remember, block shear has the net tension area, and here I've substituted for the diameter of the bolt plus 1/8 of an inch. That's going to be 7/8 inch, so you'll see that in my calculations there. We go through the calculations for block shear and we move on. We have all the net tension area, the net shear area, the gross shear area. We plug them into the equations for the block shear capacity, and we see that the block shear capacity for this particular member is 53.4 kips, and our design load was 66 kips. So that means it's not good. So we're going to have to try another section. So I want you to repeat the same deal. We repeat it for the next lightest angle. We see that one doesn't work. It has a slightly higher block shear capacity, but still doesn't work. So we try the next angle. That one doesn't work. We have to try another angle. So a lot of times in a design office, you'll have this set up in some sort of spreadsheet or some sort of software to help you keep track of the different solutions, and maybe you'll even be able to automate some of these things if you were to link it up with the properties given in the downloadable Excel file from AISC with the different specifications on the geometry for these angle members. All right, finally, let's take a look at the calculations for this member. We're now on to our 4th trial member. I mentioned that workable gauge being the minimum distance from the heel of the angle to the center line of the bolts. Again, this is just sort of a geometrical requirement so that we can actually build this connection. That gauge distance is 2 inches, and I've labeled it there in this picture. Remember block shear. Block shear has 3 different components that it looks at. It looks at fracture along the net tension area. So I've highlighted that there in red. It has fracture on the net shear area, which I've highlighted there in green. And that would be the area there through the bolt holes. And then finally we have the gross shear area, which the gross shear area would not include the cutouts of the bolt holes. And then we're going to look at, yielding on the gross shear area. And I just labeled this distance in there as 9 inches. You can go back to the original problem statement to see that distance. It was 3 inches from the edge of the member to that first bolt, and then 3 inches between the center line of the bolts. All right, so we run through our calculations. We see that this one works for block shear, so it is okay. So we've now successfully designed this particular member. Remember, this was a double angle, so we designed just one angle. We'll have to use a double angle, so use a 2L 3.5 by 2.5 by 3/8, and that will satisfy our design. Finally, there's something called built-up members. So we didn't talk about this explicitly maybe in class, but it is in Chapter D. You can take a look. Built-up members are members that have multiple shapes together. And so basically for this double angle member, in order for it to be effective so that we don't end up having some sort of intermediate failure, it looks at intermediate connectors. So in order to treat these two angle members as kind of one unit, we need to see, do we need intermediate connectors between the connections? So we look at this limitation, we look at L over R. We satisfied L over R, and we can go through and do the calculation. We see that L over the L of our connectors could be down to 160.5 inches. Our member was only 120 inches long, so we do not need to have intermediate connectors in this case. Finally, I just want to remind you that we checked the design of this member for the limit states of yielding, fracture, and block shear. We have not considered our bolt-related limit states or other connection requirements. Those are coming up soon, so I look forward to future lessons and describing them to you as well. But please make sure you just don't go and use this connection. You still need to check the bolt limit states and connection details. All right, so I hope you enjoyed doing this design and you're ready to tackle a design problem on your own. Here's a little bit more about the design process and what the future has in store for you. As you can see, there are a lot of little details when we're designing steel tension members, and I'm probably not going to be able to teach you all the ins and outs in one video or one semester of class, but that's okay. We got to start, and the problem that you got to see, we got to design a double angle tension member, and we got to see the minimum gauge distance, right? Now, what happens when we go to a channel? Well, it's going to be a little bit different. The clearance limits are going to be a little bit different. And each design is going to have its own kind of constraints. But that's the beauty about design, and that's why we like to be engineers. You have to problem solve through that design process. And don't worry, when you get out there, when you first become an engineer, you're going to be working with a senior engineer, and they're going to teach you a lot of these tips and tricks so you become a design pro. All right, that's it for now. Let's rock on. Peace out, steel friends.